Now in section 6.3 we will continue with lines and segments and their relationships in a circle. We've seen this before, but if a line goes through the center of a circle and it's perpendicular to the chord, then it's going to bisect the chord. And then we have, if we reverse, if a line goes through the center of a circle and it bisects the chord, then it's perpendicular. So if it's perpendicular, then it bisects. If it bisects, then it's perpendicular. And we've seen a picture of that several times, but here we have a circle and we have a ray here actually going from the center, and it is, here we are, it is perpendicular with that chord. That must mean that those segments are, that chord is bisected. Or if we had this ray and it bisected this chord, that must mean that they're perpendicular. And then when you put perpendicular and bisector together, if a perpendicular bisector of a chord, if you have a perpendicular bisector of a chord, then it must contain the center. It's got to go through the center. All right, let's try to see if we can find the lengths of some of these segments and such. So here we are. Here's circle O, and it has a radius of 5. Okay, so it has a radius of 5. And we are told that segment OE is perpendicular to segment CD. So we're going to put our little right angle notation in there. And we're also told that OB is 3. From here to here is 3. So we actually have right here inside this circle, we have this 3, 4, 5 Pythagorean theorem triplet, which means if they're asking us what is CD, what is the length of CD? The length of CB is 4, so CD is 2 times 4, or the length of CD is going to be 8. Here's a reminder of what concentric circles might look like. These circles share a center, but they're obviously of different radii. And if I were to have the tangent of the smaller circle, the tangent of the smaller circle is going to be a chord of the larger circle. That makes sense. But let's talk about when we have two circles and different possibilities for tangents. So here I have two circles. These are not concentric. They do not have the same center. One has center P, one has center Q. But they are tangent at a single point. They are tangent at a single point. Here we have two circles. They also are tangent at a single point. At one point. These circles are said to be internally tangent. Internally tangent. These are internally tangent circles. And not surprisingly, since these are, one is not inside the other, these are externally tangent. Externally tangent. So circles can have a point of tangency whether they're internally tangent or externally tangent. Now, an important segment that gets created when you're looking at two circles, any two circles, is something called the line of centers. The line segment that connects the two centers is called the line of centers. The line of centers here is that little segment, PQ. And notice the point of tangency is not on the line of centers. And then here we have the line of centers, and here the point of tangency is on the line of centers. So we'll be able to tell some other characteristics of two circles when we look at their lines of center and also what happens with tangencies. So the line of centers, for two separate circles, the line of centers is the segment that contains both centers. So if we look in this figure, here we have line segment AB, or it actually could be a whole line. Line segment AB is considered the line of centers for circles A and B. So a line, a segment, or a ray that is tangent to each of the two circles is a common tangent. And it may be a common, if the common tangent does not intersect the lines of centers, it is a common external tangent. So here we have, moving on, here's circle P and here's circle Q. They do have one common tangent line. That is an external tangent because here's the line of centers. For these two circles, they have actually 2 points of tangency, or two lines of tangency. Here are 2 different lines that are tangent to both circles. So these 2 circles are said to have 2 external tangents. 1 external tangent, 2 external tangents. And why are they called external? Because the lines do not intersect the line of centers. Tangent lines do not intersect the line of centers. All right, but you can have tangent lines that do intersect the line of centers, and those would be called internal tangents. A common internal tangent, common to both internal tangent or common internal tangent line. And that's when they intersect, when the tangent line intersects the line of centers. Here's my line of centers between these 2 circles. And notice the tangent line does touch the line of centers. Here's my line of centers between these 2 circles, and this has 2 common internal tangents because that line touches the smaller circle and then that line touches the larger circle. This tangent line touches the larger circle and touches the smaller circle. But in both cases, it's the tangent line or lines is touching the line of centers. That's why it's called an internal, common internal tangent line. So that was some vocabulary. Let's move on to something a little bit different. Another theorem is that tangent segments that touch at an external point, these segments are always congruent with each other. The distance from an external point tangent to the circle is always congruent.